All right. So our first speaker in this session, which is called, oh man, I'm sorry, I'm running from back-to-back meetings, Methods with Meaning, Celebrating the Why Behind Statistical Innovation. Our first speaker is Dr. Lucy D'Agostino McGowan from Wake Forest University.
Thank you, Sarah. Today I'm going to talk about the role of congeniality and multiple imputation for doubly robust causal estimation. I've recently become very excited about missing data, so hopefully this will be interesting to folks. And I also have recently become kind of cold on multiple imputation. So I'm going to tell you how to do it if you want to do it, but I'm also going to show that there's a lot of cases where a complete case would actually probably be just fine. Okay, if you'd like to find these slides, you can find them on my website at lucymcgowan.com/talk. And then at the bottom here, I have a little link to a preprint that covers all of this material as well. So I'm going to start just with a primer on doubly robust estimation in case folks are not kind of up on the on that, and then I'm going to go into a bit of a theoretical justification. So the big picture here is what needs to go into the imputation model, and it'll become maybe more clear once I go through this doubly robust primer. But it's a little bit more complicated than what you would normally think of with when you're handling multiple imputation. So I'm going to give a bit of a theoretical justification for what needs to go in, and then I'll show you some simulation results, which will hopefully help you trust my theoretical justification. So what motivated me to do this? Well, I should say kind of before even what I'm going to show here, Sarah and Stacy Hepler and I worked on a paper a couple years ago on what should go in an imputation model, in particular why the outcome should always be in stochastic imputation models, of which multiple imputation is a type of stochastic imputation model. And this sort of launched my interest in thinking about multiple imputation because I realized that I myself didn't have a strong understanding for kind of why different pieces needed to go into these imputation models. And it made me realize that there was maybe not just me, but a lot of applied researchers that also had these questions that maybe there wasn't enough literature kind of addressing. And so that is part of what motivated me to start thinking more carefully about this. But basically, there's this common oversight in applied research that folks are, myself included potentially in the past, are excluding important variables or their functional forms from imputation models. And so I have a couple examples from kind of what I would consider are some of our top applied methods journals. So for example, a simulation study that was published in the Statistical Methods for Medical Research. This study was comparing multiple imputation propensity score integration strategies. Basically, it was trying to address the question, when you use a propensity score model with multiple imputation, should you fit the propensity score model first and then do multiple imputation and sort of treat those as fixed and then integrate kind of the ultimate result? Or should you do lots of kind of imputed data sets, fit a different propensity score in each, get lots of different estimates, and then combine them at the end? So they were trying to answer this question, and it turned out they accidentally excluded the outcome from their imputation model and ended up getting entirely the wrong answer. So they actually made the wrong recommendation methodologically because it looked like the one that should not have been chosen looked unbiased because basically the two errors, the error of not putting the outcome in the imputation model and the error of using the wrong method, canceled each other out, whereas the one that was actually correct but also was missing the outcome looked incorrect just because it was missing the outcome. So there's sort of this example of trying to sort of tell us the right methods, but it had this kind of error of missing the right pieces, which then resulted in, until kind of it was noticed in the literature, it was the wrong, folks were doing the wrong thing there. Another study published recently in Statistics in Medicine, it was examining multiple imputation with doubly robust methods, and it actually excluded the exposure variable from the imputation model. And this was interesting because this paper that I have cited here, my archive, my preprint paper, when I was kind of going through the review process in that paper, someone pointed out this paper to me and said, oh, it's already been solved. We've already done multiple imputation with doubly robust methods. And I sort of was able to address it. This paper actually had kind of a grave mistake, which I'm trying to help address. So the authors attributed their suboptimal multiple imputation results to, they basically just said maybe there's some poor model fit, but the real issue was probably the lack of congeniality between their imputation model and analysis model since they had left the exposure variable out. And then there was a recent study actually that just came out in AJE, the American Journal of Epidemiology, which actually, this was an excellent, I really liked this paper. It was a great paper. It compared multiple imputation scenarios using TMLE, so targeted maximum likelihood, which is a way to implement doubly robust methods. And it found that the default multiple imputation methods often gave the wrong results, whereas methods that basically matched the analysis complexity performed better. And this totally tracks with what I would have expected. The connection there is likely because the kind of more complex ones are congenial with the analysis, but this connection between the congeniality principles and kind of why those models work better than the defaults wasn't necessarily made within that paper. So I think this is sort of what motivated me to start thinking about this. So the big takeaway that I want you to get from this whole talk is that your imputation model needs to include the outcome, for sure, yes, and must include the outcome when you're doing multiple imputation. It needs to include the exposure, so it must include your exposure that you're trying to analyze. It has to include all the variables in your propensity score model in the same functional form that they are in your propensity score model, and it has to include all the variables in your outcome model in the same functional form that are in your outcome model. So this is like the big picture that I'm hoping everyone will kind of get from my talk, and if you get nothing else, so hopefully this slide will stick with you. You're going to see this slide 2 more times, so hopefully that will be clear. Okay, so a bit on doubly robust estimation, and just for notation for the rest of my talk, my outcome here is Y. My exposure is X, and I have some pre-exposure covariates, which I've labeled as instruments, things that only influence my exposure, confounders, things that cause both my exposure and my outcome, and precision variables, things that only affect my outcome. I could also say, I said that in words, I could say it in a picture, so this is just the DAG for that same assumption here, where ZI only influences my X. ZC is a confounder, so it influences both X and Y, and ZP is precision. It influences just Y. Okay, so ultimately I'm interested in an average treatment effect, which I will summarize, or which I will use the terminology ATE. So ATE is just average treatment effect. And this is usually the kind of equation that we would use for that for an estimand to be able to estimate the average treatment effect. So I'm going to use delta as my causal effect of interest here, and ultimately I'm interested in basically the average difference between potential outcomes. So Y1 in kind of causal inference speak, we write it like this, where this is your potential outcome if you were given the exposure. Y0 is your potential outcome if you were in the unexposed group, or if you were not given the exposure. We ultimately would like to know the difference for every individual, but we can't because only one is observable, so we're going to try to kind of estimate this. Okay, a little more notation. Pi I'm going to denote as the propensity score. All the propensity score is it's just the probability of being exposed given your confounders. So ZC here is my vector of different confounders. So one way to get at delta here is through inverse probability weighting. So again, delta is my estimate of interest, and so my estimator, a potential estimator, could be this IPW. So what IPW does is it essentially reweights your exposed, so XI here would be an indicator that you're in the exposed group, and unexposed, 1 minus XI would be 1 if you're in the unexposed group. So it reweights your exposed and unexposed populations using the propensity score. So here in the denominator, I've got the propensity score for my exposed. I've got 1 minus my propensity score for the unexposed. And it's basically balancing their covariate distributions so we can make an apples to apples comparison when trying to compare Y in these two groups. So this works as long as the propensity score model is correctly specified. Another way to get delta would be the G formula, which is basically an outcome model-based approach. And so the G formula uses regression models, typically, to predict what each individual's outcome would be under exposure. So you'd fit one model here, this mu1 would be a model under for those who were in the exposed group, and then you'd fit a separate model for those in the unexposed group. And then it averages the difference between the two. So it predicts what would happen to you if you were exposed, what would happen if you're unexposed, and it averages the difference. And so this one's going to work as long as the outcome models are correctly specified. And it's got an S here because typically you're fitting two different models, a model among the exposed and a model among the unexposed. And then you're predicting for everybody out of those models. Okay, so doubly robust estimation, if you were able to internalize those equations that I just showed you, it maybe will be obvious what I'm about to say, but basically it's combining these two. So it combines that outcome modeling, so this looks exactly like that G formula that I just showed, and the propensity score weighting. This looks almost exactly like the IPW estimate, except now instead of just having Y, we have the residuals from our outcome models. And so basically it's correcting your predictions with IPW weighted residuals. This is like super smart because what will happen now is that you can either have your outcome model be right, in which case the residuals will be 0 and this will just drop out, or you could have your propensity score model be right, in which case your residuals will get reweighted and you'll get the right answer, or some combo between the two. So the reason why it's called doubly robust is because it works as long as either the propensity score model or the outcome model are correctly specified. So even though both models need to contain this ZC to be right, so these confounders, they have to have them in order to be kind of correct, the doubly robust property can be kind of useful in the sense that it ensures consistency as long as at least one of the models captures the functional form. So maybe you kind of have a better understanding of how these confounders are related to the outcome, in which case it would kind of help that you can use that piece as well. It is possible to estimate mu, that's the kind of regression outcome model piece, using both ZC, the confounders, and ZP. So ZP would be those precision variables, and that's because the precision variables can improve the efficiency without introducing bias. And there is a recent paper that actually also recommended maybe using precision variables when estimating the propensity score. And this is going to play into what I'm going to show because you can do this, but if you do, you need to be really careful to include those also in your multiple imputation. Okay, so now on to imputation. So missing data, it can occur in the outcome or in the confounders, and so we're going to consider both of these cases. And the assumption here is that the data are missing at random, so that just means that the probability of missingness depends only on the observed data, and I'm assuming that because that would be what would make multiple imputation appropriate. So I have this word congeniality in my title, and what I mean by that is basically compatibility between the imputation model and the analysis model. And so a congenial model is going to assume the same relationship among variables, which means that the same variables are included in the imputation model as all of the subsequent analysis models, and also they're in their same functional form, so either linear or splines or interactions, etc. And you'll notice here, it's typically we just say analysis model, but in this case, we actually have many models because we have a propensity score model, and then typically we have 2 outcome models. And so we need all of these to kind of match and be in that imputation piece. So to be congenial, it must include the outcome, the exposure, all variables in your propensity score model, all variables in your outcome model in the same functional form. For this piece, this is a little citation to the paper I mentioned with Sarah and Stacy that just can convince you why that outcome needs to be in there. But it's not just the outcome, everything, the exposure and all the other variables also need to be in there as well. And when using doubly robust methods with a binary exposure, you actually have to fit separate imputation models within each exposure group. And that's because of this in the same functional form piece. What's happening with the doubly robust methods where you're fitting separate models by exposure status to get that mu1 and mu0, it's basically effectively that you have an interaction with exposure. And so fitting those separate imputation models ensures congeniality with the outcome models, which are fit separately by exposure or have an interaction with exposure, because those outcome models basically are interacting the exposure with all of the confounders that you've put in them. Okay, and just so the doubly robust, it won't save you. So I think we use this term doubly robust. We think that it will always, as long as one of the 2 are correctly specified, you'll be fine. This is like what I always say when I'm teaching about doubly robust methods. We teach they require only one correctly specified model, either the propensity score model or the outcome model. But this does not extend to imputation misspecification. So both the propensity score model and the outcome model can be correctly specified, and an incorrect imputation model will give you a biased causal estimate. I think this should scare us, and maybe should scare us away from using multiple imputation, but yes, this is like very important, I think. Imputation requires more than identification. So this is another piece that I think I had not thought carefully through until thinking about this for this paper. So variables not needed for identification can still cause bias with multiple imputation. So for example, precision variables, you didn't have to put a precision variable in your outcome model. These are things that only influence Y. They don't help you estimate your causal effect, as in the actual effect between X and Y, other than improving your efficiency. So they're not needed for causal identification. But if you put one in your outcome model and you do not put it in the imputation model, your causal effect will be biased. And why that happens, I think briefly kind of what's happening is because you must include Y in your imputation model, you basically induce this conditional association between your confounders and a precision variable if you have missing data in your confounder and you put the precision variable in your outcome model. And so omitting that precision variable from the imputation model will basically create incorrect correlations that doubly robustness cannot fix. And so this is like, I think maybe even extends beyond what we would normally think of in this case. So, okay, what's happening with the multiple imputation process? What's the right way to kind of combine these pieces? You want to first specify the imputation models for the variables with missingness, and you want to specify it such that it includes the outcome, the exposure, and all of the variables in the propensity score model and all of the variables in the outcome model in the same functional form. And then you would want to generate M completed data sets by drawing from that posterior predictive distribution. And then you would fit the doubly robust estimator within each data set. So you would fit the propensity score model and likewise fit those M1 and M0 models and then combine them into that delta hat. And then you would pool those results using Rubin's rules. Okay, so let's do some simulations. So that's kind of the theory of why you want to do it like this. I'm just going to show some simulations to briefly show kind of what can go wrong if you don't. So the process that I went through, I generated data under 4 different sample sizes from 100 to 2,000. And then from that, I generated some missing data, fit the imputation models, fit the propensity score model and outcome models, and combined them into this doubly robust estimate. I did that 20 times, and so we did 20 imputations per run, and then applied the Rubin's rules to combine those 20 doubly robust estimates. And we did this, each of these steps, we did 500 simulations for each of the different sample sizes under each of the different conditions. So my Z here, my vector of pre-exposure covariates were all normally distributed. X is Bernoulli. It's based on the confounder C and the instrument ZI. And then Y is, we assumed this treatment heterogeneity so that there's this interaction between X and ZC. And then we generated the missingness such that there would be about 20% missing data for each of my Y and my ZC. And these are separate. So we never had both Y and ZC missing in the same run. That we kind of had them different, each one. Okay, so then for missing Y, I fit separately for X0 and X1. So this is where I split. This is the correct one. So the correct model would be like this. X is implicitly in here because we're doing it separately by X0 and X1. So the correct imputation model would have both ZC and ZP. An oversaturated one that we fit where basically I put splines on both of these, missing ZP, missing ZC. And then we did some that were fit to all the data not split by X0 and X1, one that was missing the interaction, and one that's missing X entirely. And then we have all these same scenarios except when ZC is the thing that's missing, so missing ZP, missing Y, and missing X as well. So here are the results. You can see here, so this is the coverage on the Y-axis. Sample size is on the x-axis. This dashed line would be 95%, which is like right where we want. On the left-hand side, I have where we're missing ZC, the confounder, and on the right-hand side, I have where we're missing Y. So the correct imputation model does what we would expect, so that's good. We're right around the nominal coverage in both cases. And the oversaturated imputation model, likewise, is giving us correct coverage. And I think this is important. That's the one that had those splines in it, which basically gets to my final recommendation, which would be just include everything as flexibly as possible if you're uncertain, if you want some like general rule to pass on to your applied biostat friends. Okay, then in orange here we have the complete case analysis just to show you that if you just have missing confounders, in most cases you have to put you have to put all the confounders in your model in one way or another in order to get an unbiased causal effect. And so actually a complete case will always be unbiased in this setting. And so this might be my kind of tirade against imputation. I'm sort of thinking that there's a chance that missing when the confounder is the thing that's missing, that potentially we should be thinking more about complete case analyses. Now, when the outcome is missing, that's not the case. And this is kind of where a lot of the literature on missing data is built around the outcome being the thing missing. And in that case, you will be biased if you do a complete case analysis.
You are at time, Lucy. If you
Oh,
could quickly wrap up, please.
yeah. For some reason, I thought we had 5 extra minutes because of
You had 20 minutes?
Oh, okay. Perfect. Didn't someone drop? No, we just had
You
20
had
minutes.
15, now you have 20.
I got it. Okay. Yeah, I'll just skip to the last one. So basically this this shows that if you're missing X, it's really bad. If you're missing the outcome, it's really bad. If you're missing a precision variable, it's really bad. And even if you just misspecify your precision variable, like if you had a precision variable that was in there as a spline, then you are super bad. Okay, the end. Thank you.
Thank you so much.
Yes.
All right. So next we have Marissa Ashner from Duke. If you want to share your screen and get started.
Yes, thank you. Can you see the presenter view or the actual view?
We can see presenter view.
Let me switch these. Here we go. Okay. Can you see the correct one this time?
Yes.
Great, thank you. All right. Hi, everyone. Thank you, Sarah, for the introduction. So my name is Marissa Ashner. I am a biostatistician at Duke, and today I will be discussing some applied work that I've been doing, and the presentation is called Predictors of Physical Resilience in Older Adults Undergoing Total Knee Arthroplasty, a biomarker analysis from the Prime Knee study. And so the contents of what I'll be talking about today, I'm going to start out with some institutional context. So where did this research problem come from? I think especially given the name of this session, it's important to kind of talk about where in the world we got this from. We didn't just kind of take this statistical set of methods out of thin air. We're actually looking at it in the context of a very real problem in healthcare. And so after that, I'll talk about this concept of physical resilience. And so what is that and how do we measure it? Then I'll talk about what we call the prime knee study. And so what data do we have to study this idea of physical resilience? Then I'll talk about what we call the expected recovery differential, how to derive that and what we do with it. And then finally, now what? So limitations and future directions after all of that is over. All right, so this institutional context, where did this research problem come from? I would like to start by just talking about this idea of collaborative biostatistics. And so at Duke, I live in this methods core called BIRD, or Biostatistics, Epidemiology, and Research Design Methods Core. And there are many different BIRD cores around the country if you've never heard of them. But essentially, we live within the Biostatistics and Bioinformatics department at Duke. And our team, basically, we all have effort across various different departments in the School of Medicine at Duke. And so each of those departments has a team of faculty and staff methodologists who work with interdisciplinary networks of clinical investigators across the school. And the idea is to form long-term partnerships with these investigators. So when they have some sort of research problem, like I'll be talking about today, we can work on different statistical methods to help them answer that research question and maybe to evolve on that in the future. We can put in more grants with these same investigators to try and collect data to help us, further those methods as well. So it's a very neat setup that we have. And so the idea is for us to provide expertise and guidance on all aspects of study design, statistical methods, implementation, and also interpretation of results. So kind of through the whole clinical research study process. And so where all of my collaborative effort lies is in the Duke Aging Center. And so that's the project I'll be talking about today, is through the Duke Aging Center. And specifically, I focus on what's called the Pepper Center. And I also live in the data science and statistical lab. And so in the what we call the DSSL, we have statisticians in these various different kind of subgroups within the Aging Center, but I specifically work in this Pepper Center. And so the idea of the Pepper Center is that we support research and training that improves the independence of older Americans. And furthermore, our goal is to understand and optimize what we call reserve and resilience. And so we'll be talking about those two things a bit more throughout the talk. Starting right now. So physical resilience, it was in the title of the talk, and it's going to be used throughout this talk. And so I want to talk about what is it and how do we measure it. I think usually when we think of resilience, or at least when I used to think about resilience, I would think more about cognitive resilience, so or emotional resilience. But what is this idea of physical resilience, particularly in older adults? And so the Duke Pepper Center has this conceptual model of what we call reserve and resilience. And so I'll walk through this. But basically, where do I want to start here? We'll start on the left. There are these different lifetime exposures, such as your medical conditions, your social support, lifestyle, or environment. And then you have what we call reserve measures. And so that would be like a cognitive reserve, psychological reserve, or physical reserve, just kind of like where are you at in your total health? Where are you currently at? What does your reserve look like? Then let's say we have some sort of acute stressor that occurs that possibly changes your health. So that could be an illness, an injury, a surgery, or something that psychosocially stresses you. Typically, when that happens, some sort of aspect of your health decreases when there's a stressor that hits. And so this idea of resilience physically, or this dynamic response, is how well do you bounce back from some sort of acute stressor, or how well do you recover from an acute stressor? And when we say that, we mean how well do you physically recover? And so we'll talk about some examples of that as we go on. But further down the line, some outcomes from this could be something like independence, which is what we're interested in studying, quality of life, participation, or survival. And so we are distinguishing between this idea of reserve, which is, what does your total health look like in general on a normal day? And then resilience would be after your health drops because of some acute stressor, or possibly even a chronic stressor, how quickly can you bounce back? How much can you bounce back? There are different ways that we can talk about that. All right, and so now that we've got a working definition of physical resilience, how do we actually measure it? How do we measure how well someone bounces back? And again, in the Duke Pepper Center, we have used two different ways to do so. And so the first one we call the recovery phenotype. And so I'll kind of walk you through this graph. And so let's say we have some sort of baseline. So this would be where you measure all of your like reserve pre-stressor things. You're at some sort of place in your health, some variable Y. You're at some level. And then a stressor occurs right after baseline. So typically your health will drop to some low point. And then we want to measure your recovery over a certain amount of time. So in this case, we're measuring the recovery over 12 months. And this person almost bounced back to where they were at baseline in this case. And so the idea of what we call the recovery phenotype here is to summarize or classify patterns of recovery over time. So we're actually looking at the whole trajectory of where were you at baseline, how far did you drop, and then how well did you recover. And so if we were to take a whole sample of people and look at their recovery phenotypes, we would typically use some sort of statistical technique like a latent class trajectory analysis to try and group people into a couple different classes of recovery patterns. And we can measure this idea of physical resilience that way. There's a second type of measuring physical resilience that we also focus on here in the Duke Pepper Center, and that is what we call the expected recovery differential. And this one is what I will be focusing on for the rest of this talk, but I wanted to cover both of them at least a little bit. And so the idea of this is how much better or worse does someone recover after a certain time point than we expected based on some clinical baseline information. So this one, you kind of see that their observed trajectory is the same as what we saw before, but we're more interested in this actual outcome versus what we predicted them to be at 12 months in this case. So that's how we define the expected recovery differential. And this can be calculated as the residual of some sort of prediction model, to talk about it in more statistical terms. And so now that we have these baseline definitions, I'm going to talk about the prime knee study, which will tell us what data do we have to study physical resilience. And so because the Pepper Center exists, and it has for a long time at Duke, the clinicians there actually did a prospective study called Prime Knee, and PRIME stands for the Physical Resilience Indicators and Mechanisms in the Elderly. And specifically, Prime Knee enrolled about 200 adults 60 years or older who underwent elective knee replacement surgery. And so this was an elective stressor. At that point, we were able to measure them at baseline, right before the surgery, and then some aspect of their health went down because of the stressor. Surgery is a stressor on your body. And then we were able to follow them afterwards to see how they recovered. And so these participants in particular were followed for 6 months post-surgery. And so what data do we have captured in this prime knee study? And it's a lot. So basically we have this baseline visit. And so this again happened before the surgery. And so we have clinical covariates, so demographics, education, social support, comorbidities, for example. And then we have all of our tests of reserve, what we're calling reserve. So we have some cognitive tests, such as the 3MS or trail making, physical reserve, such as a 3-minute walk or your grip strength, psychosocial reserve, such as the psychosocial resilience scale and the PHQ-9. We also collected blood for different biomarkers, and then our outcomes. And these resilience outcomes of interest were pain intensity, pain interference, step counts, which were measured using a Garmin watch, and then lower extremity physical activities of daily living. So one example of those would be like, for example, are you able to put on your pants independently? So that's an example of one of the lower extremity PADLs. During the week of surgery, we collected surgery covariates, such as complications and length of stay, as well as those same outcomes. At 1, 2, and 4 months after surgery, we collected some intercurrent event information, any rehab they received, and again, the outcomes. And then at 6 months, all of the reserve tests, and again, the outcomes. So we have these outcomes over starting at baseline and all throughout 6 months. So we're able to create both of these resilience measures that we talked about previously. All right, and so now we know the data, we know these different resilience measures, and so I'm going to specifically talk about that second one, the expected recovery differential. So how do I derive it and what to do with it? And again, This expected recovery differential, or I'll call it the ERD for short, is how much better or worse someone recovered than they were expected. And the expected recovery is calculated via a prediction model. And so we know as statisticians, there are many different ways to build prediction models, and we chose a penalized regression for this case. And so we chose mixing and penalty parameters using cross-validation and build the best prediction model that we could using that type of penalized regression model that we chose. And what we decided to put into the penalized regression is anything that was collected at baseline or during surgery, including clinical characteristics, reserve measures, surgery characteristics, and baseline outcome measures. So the idea was, based on all of these clinical characteristics that happened before or at surgery, what would we predict your recovery to be at 6 months? And then we compared that prediction to the observed outcome itself, and that residual was defined as the ERD, or our resilience measure. What is the ERD useful for now that we have this residual? And so the idea is that we've already teased out the impact of many baseline characteristics on the 6-month outcome. And so the ERD now represents the portion of the observed outcome that the predictive model couldn't predict with the covariates that we fed in. So some of this, of course, would be random error or individual variation, but some may be due to other factors that we didn't yet account for in the predictive model. And so this is where our baseline biomarkers come in. We want to answer the question, what biomarkers are predictive of this ERD resilience outcome? And can we use this idea to identify biological mechanisms underlying resilience beyond the clinical characteristics that we've already teased out the effect of using the residual or the ERD? And so we have a lot of baseline biomarker data. We have small RNAs, protein biomarkers, metabolomics, and lipidomics. And especially considering our sample size of only 200, how do we determine which of these many biomarkers are predictive of our resilience outcome? And so immediately, at least in my mind, penalized regression, again, is what pops up. But what would be the problem with using penalized regression here? And so, in other words, why is using a classical variable selection technique maybe not ideal? And so classic techniques like lasso, for example, they can be highly sensitive to small changes in the data. They can be very dependent on regularization or what penalty parameters you're using. And they also seem to have correlation blindness, where if you have a lot of correlated predictors, it will only pick one of them typically. And so what can we do instead to kind of expand on this and maybe address some of these potential problems? And our solution here is stability selection. And so rather than running one penalized regression model with one penalty parameter that was tuned in some way, we're going to run a bunch of models, see what biomarkers pop out as predictive, and then take the ones that pop out in the most models, and that will be our stably selected set of biomarkers. And so based on what I just said, you probably have more questions. How do we run a bunch of models? What do I mean by that? And then what do I also mean when I say these will pop out in the most models? Which ones will pop out in the most models? What does that mean? And so our stability selection pipeline is what's kind of innovative to this specific situation and something that we've developed to specifically answer our question. And so what we came up with is this. First, we're going to resample the data 200 times, and that the number 200 is a little bit arbitrary, but resample the data many times. Run a lasso with a specified penalty parameter for each resampled data set. And then calculate the selection probability for each biomarker. How many times out of 200 was it selected as a non-zero parameter? Then we're going to save the top 10 biomarkers out of from those selection probabilities, which have the top 10. That will be our stable set. So we use two different resampling techniques. We use the bootstrap, which is sampling with replacement from our data. And we also use complementary pairs, where the data set is basically randomly split in half, and each half is used as one resampled data set. We also used 5 different penalty parameters, corresponding to lasso choosing a different number of non-zero parameters each time. And so in total, our pipeline was completed on or 10 times essentially, one for each combination of resampling technique and penalty parameter. So basically what we ended up doing was, since we completed this whole pipeline on the left 10 times, we had 10 stable sets. And we counted which biomarkers showed up in the most number of stable sets. And I know I'm a little bit low on time, but I just want to quickly show you guys what the results for this sort of thing might look like. And this is an example of a table of results for our pain outcomes, so pain intensity and pain interference, and the protein biomarkers, of which we had 50 of. And we basically said, how many stable sets out of 10, so that combination of resampling and penalty parameters, did the biomarker show up in? And so we were able to say, for example, these biomarkers that showed up in all 10 stable sets, I call them the most stable, the most stably selected, and same with pain interference. Something that we took from this, these pain results, is that IL-5 was something that showed up very stably in both of them. And that was something that was kind of a further proof of a hypothesis that had already been generated in the pain literature. And so that was very cool for us to see. We also created some forest plots to see what direction the association between those biomarkers and the ERDs went. But again, I know I'm short on time, so I won't go over these in much detail, but we were able to visualize them as well. I will quickly talk about limitations and future directions and then finish up. But essentially, the limitations of this are that the entire process is hypothesis generating. We're not performing any statistical inference or measuring uncertainty because post-selection inference is already nuanced, and we had a very ad hoc pipeline that creates even more nuance for measuring anything like that. Also, our ERD model is not necessarily generalizable to other populations. It's a very sample-specific prediction model. And so future directions are essentially thinking about the meaning of ERD and whether we would want it to be generalizable. Also thinking about if we can derive valid standard errors or interval estimates. But for now, we're writing up all that we have done related to this ERD and also that other recovery phenotype that I talked about before. All right, so I know that was a pretty quick run through of all of that, but thank you. My email is up here in case anyone wants to contact me.
I think we are out of time. Thank you, Marisa. I'm going to switch over to the next speaker. So
Perfect.
I want to introduce Dr. Rebecca Hubbard from Brown University. Rebecca, you can go ahead and share your screen and get started. Thank you.
All right, thank you very much. So I will, in the time that we have available in this session, talk about a project that I worked on a few years ago. And I thought, since when I was invited to this session, I thought the title, Celebrating the Why Behind Statistical Innovation, was really provocative and kind of challenged me to think about what is the role of statisticians and scientists as people in the science that we produce, and how do we get to the results that we end up publishing? So this is going to be a kind of non-traditional, lighthearted kind of talk where I tell you the story behind a paper that we published a few years ago. Near the end of my talk, I will actually present the methods results a bit, but this is really more about the process than it is about the end result. So this is the end result that I said was not going to be the focus of this talk. I thought I'd start at the end of the story and then tell you how we got here. So the end of the story is back in 2020, I, along with a colleague from the University of Pennsylvania, Yang Chen, and two of our Penn students, Ray Duan and Jesse Tong, published this nice paper in the journal Epidemiology, looking at a simple solution for reducing bias when you're conducting an analysis using EHR data and you don't have access to precisely the outcome measure that you wish you had. So instead you have what we call a probabilistic phenotype. So it's a prediction of the outcome derived from some kind of a prediction model. I've seen a lot of these used in practice in analyses of EHR data and often used in ways that are very far from optimal. And so we developed an approach to reduce bias in analyses that use probabilistic phenotypes as the outcome. It's a very simple solution. You can make the bias correction by hand. It literally can be calculated on a piece of paper or on a napkin. It reduces bias, and it gave us a nice publication in epidemiology. So it was a victory. Everyone was happy. We published this nice little paper. The route to getting to that nice little paper was very circuitous and featured a lot of frustrations and setbacks. So I thought, starting from the point of, hey, here's a nice paper that we published, I would take you through the 6-year-long journey that it took us to get there and describe some of the setbacks, how we responded to it, and just highlight the fact that often in science, I think we celebrate our victories and don't acknowledge the fact that we struggle to get there. And I think especially when you're early in your career, if all you see are those victories and no one is unveiling the circuitous path that it took to get to the success, it can feel like you are falling behind because you don't know how other people's failures have led up to their successes. You only see the successes. So I'm going to tell you about all of the things that we did wrong in the process of trying to get that nice epidemiology publication. So 6 years earlier, so this was back in 2014, I had an idea. My idea was I want to improve breast cancer research by addressing error in a key risk factor for breast cancer, which is captured from radiology reports referred to as breast density. Breast density is an important risk factor, but it's missing for some women. It's inaccurately assessed for other women. So just like many things from the EHR, it's error prone. And what I proposed to do was develop an approach to improve breast density phenotyping, which would give us access to a higher quality risk factor, which we could then use to improve breast cancer risk prediction and consequently breast cancer research and therefore breast cancer outcomes. So I was very passionate about this idea of improving the quality of breast cancer research. And I thought it would be very exciting to be able to do this through statistical methods development. Back in 2014, I was a bit more naive than I am today, and I had this very simple vision of how we would make science better by addressing this question in breast cancer research. So I thought, okay, we've got an idea. I think it's scientifically important. I think it's statistically interesting. So what we'll do is we'll apply for a grant. We'll get that grant. Then we'll do something, some kind of like science. So step 3 here is a bunch of smart people getting together and sciencing. And then at the end of the day, science will be better and breast cancer outcomes will be improved and everything will be wonderful. Of course, that's not actually how science works. And I think if you've participated in research for a little while, you know that nothing ever goes in a straight line. And particularly when we're talking about grant funding, it's rare that things go the way that you expect them to go. So these were the aims of the original grant that I had proposed. Aim 1 was going to be developing improved statistical methods for EHR-based phenotyping. Aim 2 was then incorporating those phenotypes for a key risk factor into subsequent estimation. And I was proposing to do that via a joint modeling approach where we would simultaneously estimate those latent phenotypes along with their relationship with an outcome of interest. And then Aim 3 was conducting a demonstration project using these EHR-derived phenotypes to improve breast cancer risk prediction. So the review committee did not like that at all. They were very unenthusiastic about it. They were very skeptical of the potential for using kind of a complex statistical algorithm to derive these phenotypes and then incorporating it into breast cancer risk models. They were like, will clinicians be able to do this in the clinic? Will anybody understand it? Is this sufficiently transparent that stakeholders would trust these methods? And so It did not get a good score. The reviewers did not like it. We were sent back to the drawing board. I have found that when you get a grant review in particular, although I think this is also true of paper reviews, you go through a process of emotional response and introspection, which follows these 7 stages, which I'm calling the 7 stages of responding to grant reviews. So the first stage is hope. You got your score. It wasn't very good, but you think, maybe when I look at the actual comments, the reviewers will have found some value in what I did, and I'll be able to improve on the few things that they identified that aren't so great. So then you take a look at the actual reviews and you see the comments and you think, what are they even talking about? Do they understand anything? Are these people even experts in the field? You feel confused by their comments, annoyed. Then you move into rage, like, what gives them the right to review my work? Do they even know anything? That's the stage where I find it's usually most effective to step back, put the reviews away for a little bit, and then come back to it later when you can have a little bit more emotional distance and clarity. So after the rage step, you move into the more productive phases of responding to the grant reviews, where you think to yourself, okay, I see how maybe we weren't too clear about some of these things, or maybe this was infeasible, or we didn't identify the best approach. So okay, I think we can address this. Maybe we can make some changes here or there. Once you get deep enough into that process of bargaining and revision, I often find myself at the existential crisis stage. At the existential crisis stage, I usually say something like, I'm just going to lay on the floor now for a while. And while I'm down there on the floor, staring at the ceiling, what I ponder and what I say to myself is this even work that I want to do anymore? Or have I changed it so much to respond to the reviewers that it no longer resembles what I originally wanted to do? And I don't even know what I'm doing anymore. But usually the existential crisis passes. I pick myself up off the floor and I say, okay, we've put together a good revision. We've addressed the key reviewer comments. I'm acknowledging that the reviewers made some good points. I think I've been able to address them. I accept that this is the direction that we're going to move forward. And I go ahead and I resubmit that new version of the grant. So having come to the resubmission stage in this journey, I found that the grant that we were now proposing looked very substantially different from my original vision of improving breast cancer research through better breast density phenotyping. So in pivoting to address the reviewer concerns, I decided they were never going to buy this statistical approach as being useful for breast cancer risk prediction. So I completely threw out the idea of studying breast cancer. I said, instead, let's take a look at pediatric type 2 diabetes. In the context of pediatric type 2 diabetes, the big concern in extracting phenotypes from EHR data is really about phenotyping that outcome, identifying kids with type 2 diabetes from the electronic health records. So we've now moved to a completely different application area. Also, the variable that we're phenotyping now is no longer a key risk factor, but an outcome. And so the methods that we would be developing were for phenotyping, but then for addressing error in an outcome instead of in a predictor. So with that in mind, we put together our revised set of aims. Aim 1 is still the same. We're still doing statistical methods for EHR-based phenotyping. Aim 2 now looks kind of the same. It's about taking those phenotypes from Aim 1, incorporating them into analyses, and accounting for and properly propagating the error associated with using an imperfect variable. Now it's the outcome instead of a predictor. So we came up with a whole alternative suite of methods that we were proposing to do that. And then thirdly, it was still a demonstration study, but now it's a demonstration of applying these methods to a pediatric diabetes study rather than a breast cancer study. So, you know, there's some features of the project that remained the same, but a lot that had really changed. So we submitted that. And the reviewers really liked it. They thought this was a really relevant application area and a very feasible approach, and they liked the rigor of the statistical methods. And it was approved for funding. So yay, we're celebrating. We got the grant. Now we can go ahead and do this work. So a thing that I have noticed that happens in this process of proposing a grant, revising the grant, and then if you're lucky, ultimately getting the grant, is you've assembled a team, and as you pivot to respond to reviewer comments, the team tends to get bigger and bigger. And at the end of the day, now you've got this funding and you have to figure out how to fit this team into the new problem that you've identified. So the specific work that led to the epidemiology paper that I led off this presentation mentioning was aim 2 of the grant, how to account for error in an EHR-derived phenotype. We put together a study team that looked like 3 professors of biostatistics, a bunch of stakeholders, so 4 pediatricians who are interested in pediatric type 2 diabetes, 2 patient stakeholders, 3 biostatistics PhD students who are going to actually help us get this work done. And it turned out that we all had completely different agenda when it came to trying to get this work accomplished. I think in any context, doing science often looks like herding cats, but particularly when you've come together as a group through very different means and with different objectives and at different points in time, it can be very difficult to get the team harmonized around the new set of objectives. So it turned out that some of the faculty working on this project were still really committed to the original proposal. They still really only cared about breast cancer and didn't care so much about the new application in pediatric diabetes. Some of the faculty were really interested in that original problem of accounting for error in covariates and weren't so interested in the new problem of accounting for error in outcomes. Our poor students just wanted to be able to do the work so that they could get publications, so they could write their dissertations, so they could graduate and move on with their lives. And our funder was really committed to seeing us deliver on the deliverables that we had identified in the grant proposal. So as the PI of the grant, it sort of fell to me to try to get this diverse team with different objectives organized around delivering on what we had committed to the funder that we would do. And with a bunch of people pulling in all different directions, what we ultimately ended up doing, or what I ultimately ended up doing, was saying, well, what I care about is simple solutions that anybody can practically incorporate into their research and achieving the deliverables that we said we were going to deliver on. So I'm just going to write this paper myself. And that's how it ended up that the paper that I showed you at the beginning has me as first author, is because I ultimately was the one who was like, we need to actually get this done, guys. I'm just going to do it myself. So I'll tell you quickly in the last couple of minutes about what it is that we ultimately ended up doing. The problem that we were dealing with was that the outcome that we had extracted from the EHR data had bias, would have bias if we naively incorporated it into analyses. We didn't have access to validation data, so we had to just be able to account for the imperfections in that error, in that variable, using known operating characteristics of the phenotype. It turns out that if you have a true phenotype Y and you want to regress it on a couple covariates, but you don't have access to Y, you only have access to a prediction for Y, p hat. If you make this transformation of the p hats, you subtract off the mean p hat among true controls and divide by the difference between the mean p hat among cases and controls, regressing f of p hat on Z and W will lead to an unbiased estimate. That estimation is a little bit complicated to do in the context of logistic regression. For instance, if you picture just trying to plug that f of p hat into a logistic regression in R, you're going to get an error because you don't have a binary outcome. But in the context of risk difference regression, where we're just doing a linear regression, it's very straightforward to make this correction. We can just substitute in f of p hat, solve everything to get p hat, expectation of p hat by itself on the left-hand side of the equation. And we see that there's a very simple correction that we can make to our regression coefficients to remove the bias that's due to using the imperfect outcome. That's super simple because it's in the linear regression context. We also showed that in logistic regression and in relative risk regression, you can do something very similar just by doing a Taylor series expansion of the left-hand side of the equation. So altogether, it's a super simple correction, gets you something you can do by hand and reduces bias in your analysis. So in the interest of time, I'm not going to explain the simulation results a bunch, but basically we looked at phenotypes that had different levels of performance, and we found that if you just naively throw your imperfect phenotype in as an outcome, you get bias. But if you use the bias correction method that you can just calculate on a napkin, you can remove all bias. So I just want to make a couple points to wrap up and conclude the session. From the perspective of a statistician and a scientist, math is easy, and we're taught to do it in graduate school. Dealing with people is hard, and we are not taught to do it in graduate school. As you make progress in the field, what you find is you have to deal with some really difficult people. You have to communicate ideas to diverse audiences, often talking to people with very different backgrounds all at the same time. And so you need to develop persistence, perseverance, hope in the face of setbacks, patience, compromise, and so on. And the point that I really, really want to make in this talk is that we have the ability to determine our own landmarks, to craft our own victories, and to write our own narrative. So my little stick figure over here hasn't made it all the way to the top of the mountain that he was hoping to make it to the top of, but has decided just to plant the flag here and declare a significant finding has been found. That's what I decided to do in this project, was declare that our epidemiology publication is what we always were hoping to achieve, and that was our victory and our success. And that's something that you can always do. You can always write your own story and tell your own story. And I hope people learn something from my challenges and setbacks. So thank you.